So I'm going to give you a quick idea of what's involved in Chapter 8, so you have an idea of the overall sense of the chapter itself. So Chapter 8 starts with potential energy, which we've already talked about. It then talks about conservation of energy. We talk about mechanical energy versus overall energy, and we talk about work done by an external force. So Chapter 8 is very much like Chapter 7 was with energy again. Okay, with energy. Now, something I want to point out is that I use PE for potential energy. Your text and AP exam uses capital U. So I'm going to try to adopt that nature so you guys can see it a bit better. Okay, and U is equal to mgy. Okay, and this is gravitational potential energy. Gravitational potential energy. And then the other U we already talked about, which was energy stored in a spring. Okay, energy stored in the spring. And I called that elastic energy always. Okay, if you want to call it UE or just U, that's fine as well. All right, and this last point, let's take a look at this theory here. This last part is very unique because we've talked about the change in kinetic energy and work. This next theory or this idea is that the change in potential energy is equal to the negative work done. Okay, is equal to the negative work done in this problem. And if you think about this, if I were to think about an object moving from here up to here, and I think about the work done from here to here, if I were to do that, I might have a force being applied by a cable lifting it up a certain distance. But we said a moment ago that if you're lifting an object up, what kind of work is gravity doing? Gravity is doing negative work because it's pulling down. So that's what we're seeing right here. That the potential energy gained by something is equal to the negative work done by gravity. Okay, so that's the concept of the theory behind this in this chapter. So that's really section 8.1. 8.1. Now, 8.1 goes into a little more detail, and I'll explain the problem that's going to matter to you guys for the exam about this scenario. You've got a person sitting here at the top of something, and it takes that route, or that route to end at the bottom. So here's the first object right there, and it ends at the very bottom. And the theory behind this is taking which path will cause the object to gain or lose or more potential energy or do more work. And the idea behind it is that really, what are you doing? You're changing height by the same amount. So no matter which path you take in this problem, you really do gain the exact same amount of energy. And this concept is called conservative forces is what it is. So in this case, we'd say that gravity is a conservative force. Which implies that the path taken does not matter. So if you start with a certain amount of potential energy, and let's say that potential energy is 36 joules, and you end with a potential energy of 0 joules, whether you took the top path, the middle path, or the bottom path, the work done is still going to be the same value. The change in kinetic energy is still going to be the same value. Now, if I look at this problem, right, and I think about the final minus the kinetic, final minus the initial for potential energy in this problem, we want to recognize here that we're looking at 0 minus 36. Right? So if I say final minus initial equals the negative work done, this is really going to be 0 minus 36. And we look at this, we see, negative 36 joules of work is done, and that equals the negative work. So what kind of work does gravity do in this problem? Gravity does positive work. If you want to put a G for work done by gravity for all of these, you can. Okay. Gravity does positive work here because which way is the object moving? It's moving down. It's moving down. That's where the negative sign comes from in this theory right here. Now, personally, I think it's very confusing to remember the negative, the double negative. So I'm going to show you guys a way that I attacked these problems when I was in your seat in high school. And I think this method is a lot easier. And the idea really is just go right to conservation of energy every time. Go right to conservation of energy. And the theory behind conservation of mechanical energy we'll talk about first is the following. The conservation of mechanical energy tells me that the energy in the system initially will equal the energy in the system at any other point in time. You can say initial and final. I haven't been using F for final, but the book suddenly is using F here, so I'm kind of using the F as a subscript. All this means is that at any moment, the total energy in the system is conserved. So let's look at that same example here. Okay, here's the object in the beginning. Here's the object at the end. In the beginning, let's say it's got energy of 15 joules in potential and no kinetic. Okay, 0 in kinetic and 15 in potential. That's a capital U, not a V. I hate using U, sorry. It's a capital U there. If we want to figure out the amount of energy at any other given moment, all we need to know is how much of one of the energies we have. So if I tell you a couple of meters in that we have 3 joules of kinetic energy now, how much potential must we have? We must have 12. Because again, at any moment in time, the total mechanical energy is conserved. It has to be equal at any moment. So then we go to the next part.
This is without friction.
Correct. Mechanical energy. Friction is different. That's where we're going to talk about thermal energy when we get to that. So this is all about without friction here. So let's say the kinetic is now 5 joules. Means the potential must be 10 joules. This is not drawn to scale, obviously, height-wise. And then at the very end, we'll say that it's all kinetic, and therefore potential equals 0. Okay, you definitely did this at some point last year, whether you were in my class or the other class, because you had to have seen conservation of energy. And the concept, though, is that at any moment you sum them together and it equals a constant. It equals a constant. Okay, and again, this is mechanical energy. Mechanical energy. Okay. That's 8-1 and 8-2. Yeah, Max, go for it.
So, once it gets to the bottom,
Uh-huh.
I guess this involves friction, my question. Because it wouldn't make sense to have
Of course.
15 kinetic.
Totally, Max. And we're going to talk about that. So that's kind of what we're leading into right now. So the question then becomes, what if your energy in the beginning and the end don't match up? What could have caused that? And that's going to be work done by friction. So as a result, if we knew the distance traveled along this arc length, we knew D, we could find the force of friction by figuring out what the work missing was. And let me show an example of that, okay? So let's do the same kind now. And let's say in this case, the sum of energy in the beginning equals the sum of energies at the end. So this is all types of energy now. So we've got potential in the beginning, kinetic in the beginning. Now, in the beginning, actually, we're going to say, here's how I like to put it. We're just going to leave it like that. And then we're going to say the following. We're going to say we have potential at the end, kinetic at the end, but we also have work done by friction. Last year I used to call this Q loss. If you remember from last year, Q loss was the energy done. Your book doesn't use that phrase. Your book, I think, if I'm correct, just uses W for work done when they talk about it. If they even do they do it? Let's see. They call it E thermal. So I'm going to call it E thermal. And that's exactly what Max is asking about. What if we lose energy to friction along the way? Maybe we have 15 joules to start, and then at the end we've got 12 joules plus the energy that's left over. It means that we lost 3 joules of energy to friction. And if we know that this turns out to be 3 joules, well, that's the work done. All right, that's really the work done. So this becomes 3 joules equals the force of friction times the distance traveled. And then we could solve for either one of these two variables. Either we solve for friction or we solve for the distance traveled along the arc length. We're going to get into this one more next class, okay? So chapter 7, practice, get started on the homework board, please. I will try again, as I've done in the past, to send you also AP old problems for multiple choice or free response. The multiple choice that you guys do on the slideshow ones are pretty much AP level problems. The free response, though, I like to give you old example problems. So I'm going to search for more of those, especially now that you've covered a lot more. Now that you've covered kinematics, we're going to do something that involve energy and kinematics together. Okay? Talking about chapter 8, which is conservation of energy involving also potential, and also involving work done by friction. Some sort of thermal energy losses. Okay, so that's the additional part that we're adding to this. You should have recognized by now that chapter 7 and 8 are really the same chapter. Okay, it's all about just different types of energy and the concept of conservation occurring in those circumstances. So 8 only incorporates potential and thermal energy. Now, I'm also going to go into a little bit of detail about what are called potential energy curves or graphs. I'll spend a little bit of time on that because it does show up as a possible in multiple choice. Yeah.
Just a quick question for clarification. Is the sigma E for energy? Like
yeah, total energy. So total energy initially equals total energy at the end. Absolutely. So we're taking the chapter 8 approach where we have some thermal energy losses as well. Okay, and now recognize that that thermal energy loss means that, hey, if we start with 15 joules and end with 12, we're just missing some. Okay, we're missing some, and that's the energy that's thermal, which is 3 joules. And since we know that friction is FF times, or work done by friction is the force of friction times the distance, we could say, well, those 3 joules that are missing equal this. So whether you are in today's lab, you guys did, you finished up with Alex, and who was the group that launched the projectile straight up into the air? So whether you're doing that, and determining FF, the force of drag, though you guys would call it, because you know the distance it travels. Or you guys are doing the one where you drop it. And the distance, you know that length of the track. So you could figure out, again, the force of friction based on the difference. And yeah, you guys would pick up, that's literally what you are doing. Yeah. You're finding the work done because you know the potential energy you started with, and then it's losing all of its energy to friction when the cup gets starting to drag along the surface.
It's kind of like a sinus motion, but is the W supposed to be like rounded like that, or is
This?
Yeah.
I just got lazy. Yeah, I mean, you could.
Because sometimes there's
It's
like
not omega. Lowercase omega is this is lowercase omega. Sorry, so this should be like capital W for work. Okay? Yeah, it's capital W for work, or you could think of W as watts as your unit for power. All right, so let us see where we're going to continue with. So I want to do an example. I'll tell you where I'm referring to. Let me know, please, right away, and remind me at the end to give you your quizzes back. Okay, I'll give you a quiz from chapter 7. Let me know, please, if you did this with Alex, because he said today that you guys finished up your data collection in about 30 minutes, and then you spent the last 20, 30 minutes looking at a couple of chapter 8 problems. So I don't know which ones you did. So if you just let me know if you did it already, so don't repeat a problem, please. So the one I would like to look at is, where is it? On page 198 to 199. Okay, page 198 to 199. I'm going to go back to my method of taking a quick picture of it because I think it was easier than importing the other part. So, give me a second. Oops, right here. Okay. Do we need the figure at all? I don't think we need the figure. No, we do not need. It says in the figure, as seen in the figure, we do not need the figure for this problem. Okay, let's use this photo. Let's crop it. How do I crop it? Here we go. All right. There it is. So I know it says figure. We do not need the figure. Okay? I'll tell you what the problem is. So here's the problem. God bless you. Here's the problem. It's a water park, and you're looking at a coaster, like a water ride, where you go down in a tube. Okay? And the problem is this. You're given enough information in the problem about energy, and they want you to figure out the distance traveled throughout the path of the water ride. Okay, the distance traveled throughout the path. So before I even begin this problem, the general idea is this. Here's the starting point. Here's the ending point. This is literally what's happening. Okay? And it's some weird shape, so you can't approximate it with like calculus. You're not going to be taking the arc length and curvature of each part. but instead we're going to figure out what is the distance of this path taken. And remember, for conservative forces, the distance the path taken doesn't matter. So if I think about potential energy, if I start and do that, or if I do this, ready? No matter which path I take, I'm losing the same amount of potential energy. Let's make that clear in our heads. Potential energy is a conservative force. It does not matter the path taken.
But instantaneously, it's different, right? Like,
Sure, yeah, absolutely.
Yeah.
So at this instant, it's different than at this instant.
Okay.
Yeah. So after like 2 seconds, they might be at different heights. But from the beginning to the end, because they both start at the same height and end at the same height, the delta PE is the same no matter which path we take. The change is the same because it's conservative. What, though, is not a conservative force? What is our easiest example? I think we spoke about it last class. What's the easiest one? Friction. And that one's more obvious, right? Depending upon which path you take, you may or may not encounter as much friction as the other path taken. That's your ask.
So while your PE or your delta PE will always be the same, your delta KE and delta TE will be different.
Actually, delta KE is the same also. Delta KE is exactly the same as well. Because we're changing, well,
What happens if you have even greater friction force?
if you what?
Even greater friction force with your delta KE. Or
If you have a greater friction force, the assumption is that the frictional coefficient is the same throughout. Mu would have to be the same. And KE is really a result of your PE and thermal energy.
yeah, which TE would be equal to
So I guess 'cause
friction,
thermal-
friction or thermal energy.
So is kinetic considered, it's not a non-conservative force though, because the path taken for kinetic energy at the end doesn't matter. Like if you take a ride like this versus a ride like this,
Yeah.
and there's no friction involved,
Well,
the
that's-
delta kinetic is
yeah.
the same. So the minute you introduce the non-conservative force, it changes things up. But the easy one to think about is friction as the non-conservative force, because the path taken really matters a lot. So let's see what the problem gives us so we know where we're headed. Water slide, it's shot by a spring. So the very beginning, there's a spring actually. So this is really what the problem looks like, okay? That's the very beginning of it. There's a spring that's compressed like a pinball machine, right? You pull back on the plunger and let go, and the plunger launches the pinball. So that's the very beginning of the problem. It says, down to ground level, as the glider then moves along ground level, it is gradually brought to rest by friction. So here, it hits the ground, and then it's gradually brought to rest by friction. So this might be some distance D. We don't really know. What does it say? Through what distance L does it slide along the ground level? So let's call that L at the very end, and it was capital L, so I'll use capital L. Let's see, what else? What else? The total mass of the glider and the rider is given. The compression of the spring distance is given, how far you compress it. The spring constant is given. The initial height is given. The coefficient of kinetic friction along the ground level. So it turns out that this problem doesn't have friction along the path, actually. The friction occurs at the end of this problem, not along the path. We can vary it slightly in a moment and see how that would change if there were friction along the path taken. But this problem, there's only friction acting in the blue highlighted region there. That's where friction is occurring. So it wants to eventually come to rest. So, for a problem like this, it is very tempting to want to use the word kinetic energy theorem at the end and say, well, it's going to gain a lot of energy because of the potential energy it has from gravity, because of the potential energy stored in the spring. All of that energy is going to be converted into kinetic at the end. We could then solve for kinetic and say the kinetic energy is going to be lost to friction until kinetic energy is 0 when it stops. But we could really just say to ourselves, let's call this the beginning. And then at this point in time, all the energy it gains can be transferred into the work done by friction. So you can kind of ignore kinetic energy in this problem altogether. You can kind of ignore kinetic energy. You can say that it's gaining energy along the way down. That is kinetic, and then it's being lost to the work. But why have to deal with kinetic in the first place? We don't really need it. I see 3 hands. So I'm going to go Max, Tristan, Spence.
Are water slides really frictionless?
They're not, but they're close enough while you're on the water, because the way water works is the water stream, the flow rate of the water creates a boundary layer there between the water and the rubber, and the water is actually propelling the rubber forward. So it's kind of like when a car rotates and you have static friction between the tire and the ground pushing it forward. So when you're gliding down the water is moving with you. So the friction is really between the water and the actual slide, not the water in the tube. You see what I'm saying?
But does it feel like, is it so close to being frictionless?
That's what
that it
the
feels
assumption is
frictionless?
made here. Yeah, but there is definitely some resistance between the water and the water slide. But between the water and the tube, the water is pushing you with static friction. Really, it's like a buoyancy force, if you can think about it that way. With buoyancy pushing it up, and then friction propelling you down between the water and the rubber tube itself. At the end, though, they're saying that you're landing in like a landing zone, which slows you down.
So like, we're assuming like since the potential energy at the beginning equals the kinetic energy at the bottom, I could just apply the potential at the end.
Yeah, did you hear what he said? The potential in the beginning, from the spring and the height, becomes all kinetic right here, but then the kinetic becomes all thermal energy lost to friction at the end. So why deal with kinetic in the first place? Let's go right from all the energy in the beginning to losing all that energy to friction at the end. That's exactly what we're going to do. Good approach.
And then for the beginning of the system, we have 2 forms of potential energy.
2 forms, yep.
Gravitational and spring.
And spring. Absolutely right. Very good. So we've got sum of the energy in the beginning equals the sum of the energy at the end. We know that in the beginning we have potential energy due to gravity, and we have potential energy due to the spring. I'm using E for elastic. E for elastic. Spring has elasticity. Again, though, at the very end of the problem, we've got kinetic energy here. But what's going to happen again is that this kinetic energy is going to all go to work done by friction. So really, this is going to be the energy due to thermal. Your book uses E thermal. I'll use that for now. Okay, you could also just call that W, work. So all the potential in the beginning is going to eventually all become thermal at the end.
This is more conceptual. Since like the conservation of energy, I assume thermal energy doesn't turn into potential energy again or kinetic. So where does that go?
Where does it what?
Where does it go once it cools down?
So the energy itself that it had here, where does it go?
Yeah.
Once it
Cools down.
loses all of it, it goes into the earth. It goes into the atmosphere. So a lot of the time what happens is it becomes what's called internal energy. It raises the temperature of the tube. That temperature of the tube, the raising of temperature in the tube is gaining energy. Think back, chemistry, you learn about like temperature is the average kinetic energy of the molecules. So when the tube slides along the floor and heats up, that is kinetic energy in the molecules. That the book calls it internal energy. It's a general phrase that makes it easier than saying what's really happening. But it's really the molecules and the actual temperature that's rising. Now, technically, if you've ever done this before, and you land with something that's rubber on a surface, it'll make a sound also. So that's also energy. To create sound, you're using energy. When you take a ball and throw it off the wall, and it hits the wall, some of the energy is lost to the deformation of the ball. But some of it is lost to the sound that you hear. So there's a lot of different things that energy is lost to. The book lumps them together into either thermal energy or what they call internal energy, when it gets physically deformed. Like when you dribble a basketball. Every time it lands, the ball compresses. That's internal energy that's being gained by the ball. Where is it coming from? It's coming from the potential energy of the ball when you're dropping it or throwing it or whatever. And kinetic at that point too. So we want to figure out this length L. That's our goal, is to figure out the length L. So let's see what we've got. So we've got potential in the beginning due to height. I'm going to write that. We've got potential in the beginning due to the spring. And I'm going to use D here because they give it as D in the problem. Instead of 1/2 kx squared, they give us the compression distance D. It's given as D in the problem, so I'm going to use D instead. And actually, they give us H also. So instead of using Y0, I'm going to call that H right here. See where I have Y0? I'm going to change that and call that H. Simply because they tell us the initial height, H. So I'll call it MGH. Yeah, right.
Would it be negative thermal? Would the negative thermal?
So here's the thing. This is one of those 6 and 1/2 dozen things. If you think of thermal as negative, then the positive here plus the thermal as negative equals 0. Or you say that the energy here equals the energy gone into thermal energy. You can do it either way. It's totally up to you which way you want to approach.
Oh, okay.
You follow what I'm saying?
Yeah.
So if I were to think of energy as thermal being negative, I got to put it on the left-hand side of the equation. All the positive energy it had, all the negative energy it's losing, ends up to yield 0, meaning no loss or gain in energy, just transformed. Remember, that's one of the key laws here, that energy cannot be lost nor gained. It can be changed from potential to kinetic, from elastic to potential, from elastic to thermal, from potential to internal. But it's all about how the energy changes. You don't really lose or gain energy, though, in a system. The energy in a system is conservation of energy.
So when going back to what you were saying before, so when you jump, is that the compression of the ground pushing you back up? And then is there also momentum in that of like you moving your legs up?
Yeah, so you're going to notice after this chapter, we're going to start momentum after the next test. We're going to do all linear rotation momentum we're going to get into. And momentum is very much related to energy. And when you actually push off backs, the floor is a spring. The floor is actually bending and it's propelling you upward.
Is that it, the only thing pushing you up? Or?
Well, I mean, your muscles, the actual force from your muscles is also propelling you upward. But the floor itself does bend when you push off of it.
But there's no like momentum of like, I don't know.
So momentum and energy are two different things. So when we look at momentum, we're going to see that we can use laws of conservation there as well. But for these problems, we're only looking at energy right now. But momentum is involved in anything. Whenever there's a change in velocity, there's momentum change. Because momentum is m times v, not mv squared or 1 mv squared.
So if you had like a ground that couldn't actually compress at all, could you not?
No, you could. What happens is the ground supplies a force, and the impulse momentum theory is what changes us. We're going to get into that more next chapter. But momentum impulse theory is force times time equals delta mv. And that tells us that if the ground supplies a normal force pushing back up for a certain amount of time, that gives us momentum. But we're going to get into that, I promise. You probably saw it last year, may not, may have. Yeah.
Is potential energy relative?
It is a relative.
Like at the top of the water slide, the person to like the actual floor, it's basically 0 because they're on it, but relative to the actual ground, like the earth below them, there it is.
Always relative for potential. That's why with potential energy, you always start a problem with what's called a potential energy reference line. So for this problem, we're considering this to be ground level. So we could even write, I used to write this last year a lot, P equals 0 at the bottom of the problem, to indicate that the potential energy it has at the beginning is really relative to the ground itself. Okay? To the ground itself. Very good questions, guys. Very good questions. So at the end, because it's thermal energy, we have work done by friction. Yeah?
Like a macro level, like if you're standing on Earth, is like the crust of the Earth a spring?
Yeah, technically. Anything that you jump off of or anything that you push on that deforms, you can be those things can be modeled as a spring. So anything is a spring. Even the strongest materials under any force technically have some deflection, some slight deformation. You just don't see it. Think of a diving board. You know, when you jump off the end of a diving board, it does that, right? Everything does that, literally. If I push on this pencil, I've just deformed it, but barely. And my hand acts as what's called a damper, so it doesn't vibrate or oscillate. Whereas a diving board, when you go off the end of it, it's right? Until somebody like touches it or until over time it dampens itself due to air resistance, due to internal forces. So anything you move on is a spring, really.
If there was no air resistance and you did that, it'd just be like going like that forever.
Not just air resistance, it's also internal energy deformation that's causing its energy to be lost or transformed, I should say. Spencer.
Don't they do that in buildings? Like the high wind?
Yeah, they're made to be oscillating, absolutely. Those buildings that like high elevations buildings, they have to be able to oscillate back and forth because the winds are so great. If they didn't, it would be a system that would eventually fail. So they plan for oscillations in all these buildings, absolutely, yeah. Earthquake zones, they do it too.
Would the building be considered a spring in that sense?
Yeah, it's a cantilevered beam is what it is. We haven't even talked about that in engineering yet. But cantilever beams are things like the flagpole or the diving board. That's a cantilever beam. It's fixed at one end, the other end is free. A building is a cantilever beam rotated. Think about it. Like a road, you know those signs you drive past on the highway? Those billboards? Billboards are cantilever beams. Trees, Trees are cantilever beams because they're fixed at the ground, and the top of the tree sways back and forth. So buildings have been modeled off the concept of trees where there's a core down the middle that provides some sort of resistance to that oscillation. So you see new buildings that are built, they have a mass down the center of it that absorbs any vibrations from earthquakes, from high winds.
Yeah, like the giant, the tallest residential building.
South of Central Park? Yeah.
But yeah, like some buildings have like actual like balls suspended in them, so they like move
Yeah,
the
that's
top.
so
And those are absorbing the oscillation. They're literally taking that change in energy or momentum and absorbing it for themselves so the building doesn't have to. All right, so energy due to thermal energy, this is friction times the distance. In this case, I'm going to call that L. Okay, I'm calling it L on purpose because I already defined D as the distance that the spring compresses because the problem gave it to us as D. So please recognize, people, that even though work is F times D, when you're on an AP exam, please don't call this F times D if they're using L. And especially because a lot of your exams don't have numbers, right? It's all in variables. So if I wanted to solve for the distance L through which the glider slides, you're done with the problem. Divide by FF and you're literally done at this point. Now, are we giving mu? Is that a value?
Yes.
Mu is given. So I should, because I'm giving mu, replace FF with mu Fn in general. Mu K in this case, yes. So L is simply mgh plus 1/2 kT squared divided by mu Fn. Okay, divided by mu Fn.
Could you just write mg instead of that then? Because there's no.
In this problem, yes. Yes. Fn becomes mg. And you would have to do that to solve it. I think they give you the mass, right? Yeah, look, they give you the mass here. So you would have to use mg instead. I'll underline all the givens in the problem. Okay, so yeah, you could replace this with mass times gravity. Why can we replace it with mass times gravity? Because, again, the friction force is acting along this horizontal segment of the portion. So you know that the normal force pushing up is equal and opposite to the gravity pulling down, mg. So let's pause for a second. Don't do the answer. Let's just pause. If we did this problem the first way I was talking about it, right? And I asked you guys to figure out friction along the track, could you find something like L if you were given mu? Probably not, because Fn is a function of the angle now. So if this rider, watch the rider, as the rider goes down the slide, look what happens to Fn. Which way is Fn pointing right now? Yeah, good, Matt, there it is. Fn is pointing perpendicular, and then what happens? Watch. Follow my hand. My hand is literally Fn. Fn keeps changing as an angle. So if I gave you a problem and asked you to find the length of the track and told you a mu k value, this would not work very well, right? Because Fn, which is going in here, would not just be mg. Right here it's mg, but right here it's like mg cosine theta, mg sine, you know what I mean? It's going to keep changing. So in a problem like this, where the path taken is curved, you would have to be given the overall FF value in general. Like the average force of friction is 12 newtons. Yes, friction changes as you move. Think about it logically. If you were to drop off with a tube, like a free fall straight down, very little friction. Right? Think about an inclined plane. As the incline changes on the inclined plane, friction changes. The lower the incline, the more friction is. The higher the incline, the less there is friction. So the force of friction is changing as we change the curvature of the path. So for a problem where you were determining the length of the curved path, you would have to be given an average force of friction. You would not do this. You would just plug in a number here, like 20 newtons, and then solve for L. Does that make sense what I'm saying right now? Again, because friction is changing as you go through the course. But if we get an average value, we can plug it in instead. If we were looking at the whole course, not this segment only. Matt?
This is like completely unrelated to this. There was a question on the homework, and it was talking about like an elevator and like the amount of work it did. and it was saying like the force that acted, it said it was moving at a constant speed.
Okay.
So there was no acceleration. But the force that it used was the force due to gravity. And I was wondering to like why that was the
Yeah, so even though it's moving at a constant speed, it's moving at a constant speed because gravity pulling down is equal and opposite to the tension in the elevator cable. So when you look at the problem, you can say the work done by gravity is negative because gravity pulls down and the distance d is up. So that's 180 degrees.
yeah.
But the work done by the tension in the cable, the tension pulls up, the direction of motion is up, so that's positive work.
Yeah.
So the positive work done by the cable counteracts the negative work done by gravity. So the net work done in the end is only going to equal the change in the elevation. That's all. So if you start at the ground and at the top, it means that say your delta PE goes from 0 to like 100 joules at the top. It means that the work done by the cable is 100 joules more than the work done by gravity. It's just a balance, that's all it is. So throughout the course of the problem, even if it's a constant velocity the entire way, you're still gaining potential energy, which means that the work done acting up must be more than the work done acting down. The work done acting down, gravity, the work done acting up, tension.
Yeah.
Okay, so you'd be comparing those two values. So let's take a look at this and just get a generic solution for it. All right, so it's going to be again mgh plus 1/2 kd squared all over mu mg. Okay, that's what our length L would be in this problem. Let's pause and let's go to another problem now. I'm going to talk to you more about one with path taken, okay, versus the end of the problem here. By the way, your part 2s, your free responses on the AP exam, a lot of them involve the end of the problem where the projectile or the object slides along a surface and stops. This right here is so common in the AP exam. It'll be like something else, maybe it'll be like a pendulum we haven't gotten to yet. A pendulum hits an object, moves it, or there's a conservation of momentum when an object hits another one and it takes all this stuff, or it's a projectile launch and then hits the ground. But the end of a lot of problems involve something coming to rest while sliding along a friction surface. So that's going to be this right here. Okay, work done by friction at the end of the problem. It happens a lot. Now,
So is that gonna be like a general formula at the bottom for if it was sliding?
this is a general formula when it starts with a compressed spring at a given height. You follow what I'm saying?
Yeah.
So like, can you answer that as a general problem? Sure, for that specific type. Like, so it's not really a general problem. If I had all kinetic energy, right, it was moving with kinetic energy, like you guys did with the marble. Where's the marble group? The marble group, right? Oh, yeah, there were two marble groups. Sorry. So the marble group with the cup,
Oh, yeah.
you guys had potential at the top, right?
Yeah.
And then when the marble reached the bottom, it was all kinetic.
Yeah.
And then all of that kinetic turned into thermal. So you can think of that problem as kinetic to thermal, or you can think of it as potential in the beginning to thermal at the end and ignore the kinetic in the beginning altogether. But it depends on what you're given. So in a problem on the AP exam, if you're given something about kinetic energy, then it becomes 1/2 mv squared equals mgl mu k. You follow what I'm saying? Okay, so it depends on the scenario that's given. But you know what the general problem is, Matt? Right here. That's the general problem. And I know you don't, it's like annoying to hear that. I get it, like, okay, that's great, that's what it is, but that really is. That theorem tells us everything. That energy is conserved. Energy is conserved. Okay? All right, let's do another problem. Good questions on those guys. Let's do another problem. Let's look at, where am I? Yeah, let's look at number, I'm going to make sure there's kinetic energy involved. Hold on. Looking at your conservations, but I want to have kinetic energy also involved. Well, let's generally look at the pendulum real quick. Let's generally look at the pendulum problem, because I'm realizing a lot of these involve pendula, and we're going to get to those. Okay, we're going to see those more with oscillations also. But let's start with the pendulum problem. When a pendulum is released, what kind of energy does it have when it's released? The moment it's released? Okay, so it always has potential to start Then when it reaches the bottom of its path, if we consider the bottom of the path ground level,
Maximum K.
that's when you have all KE at the bottom.
This is no air, or
No drag. Yeah, no drag. And then again, when it gets back up to here, it's potential. So this is Newton's cradle, right? Newton's cradle. And Newton's cradle is that thing you see on science teacher's desk where the balls just bounce back and forth off each other. Now, when those marbles actually collide, though, you have some energy loss because you can literally hear it, right? It goes back and forth. You can hear it. Energy loss to sound because of the collisions. There's also some air resistance. So will a pendulum ever reach its initial height? No, it will not. Unless
Another force action.
no air resistance or max.
Another force action.
Yeah, unless you push it in the beginning. But if you push it in the beginning, what kind of energy are you giving in the beginning in addition to its potential? Kinetic. So in that circumstance, it would. So, and you can see it here. I mean, I guess we could use yours from engineering class, so you can see what we're doing here. So this was just a simple pendulum that they built for part of their group Goldberg, but I kept it thinking like, hey, this is kind of we didn't use it. So if you were to, it rotates a little bit, right?
yeah.
It's all right. So if you were to release it from here, and we could do it, I have a bigger one there. If you were to release it and let it come back, it's not going to reach back to where it started, right? Look, it's getting less and less each time. And it's barely less each time. I'm getting to here. Let's see.
It's like the video of the kids sitting in the seat.
Yeah. And I have one that's, see that, look up there, guys.
It gets hit by it.
See the top up there, there's an eye hook screwed into that piece of wood coming off. And if you had me last year, you guys all saw this. I did the same thing I'm doing with a bowl, with like a bocce ball. It's about this big, and I bring the bocce ball all the way across, and I release it from like right here. And I ask, like, should I be worried on the way back? Is the question I ask. And you're never gonna be worried. It's not gonna really. I got nervous there. You see that? It looks like it's gonna hit you though when you're doing it. An MIT professor does it. And it's really cool. He actually has one that they hook up to a ceiling in an auditorium, and it's literally like a wrecking ball. It's the size of a wrecking ball, and he jumps on and rides on top of it to prove that the energy is independent of mass. Because if you think about it, in the beginning it's mgy, in the middle it's 1/2 mv squared. So if you equate mgy equals 1/2 mv squared, mass drops off. So it turns out that if you want to find the velocity of a pendulum at the bottom, the mass doesn't really matter. Okay, and that's assuming though that there's no air resistance, no energy loss.
So if there was like one of these in a vacuum, would the sound aspect, the energy loss of sound not exist, or would it still exist but just no sound happen?
There's no sound in the vacuum.
Yeah, so like
So
there
could
is-
there be? There would be
so there would
energy
be no
loss,
energy loss as a result of sound.
not due to sound and not due to air resistance, but there would be energy loss due to something else. Friction at the top.
Oh yeah.
When this string literally just moves back and forth, there is some frictional loss right here. So there will be no air resistance and no sound loss at all in a vacuum, but there would be friction due to the two materials rubbing across each other. Okay, not air resistance though, different than that.
Yeah. Is sound caused by air resistance?
Sound is caused by some sort of deformation. So air could cause sound, like literally contacting the surface could cause sound, but sound has to be transmitted through sound is a mechanical wave. Yes, it has to travel through a medium pretty much, whereas light does not. Electromagnetic waves are not mechanical waves. They don't have to travel through a medium. So sound needs a medium, which is why if it's a vacuum, there wouldn't be no sound. But yeah, sound can be caused by air, by like a pulse from air, like a sound wave, like literally what is this called? Like a sonic boom. You know what that is?
Oh,
When a jet passes the Mach 1 barrier at the speed of sound, it creates an actual sound because it's distorting the air around. So yes, it can be caused by air, it can be caused by contact. Yeah, you had your next one.
So the only way you could have basically a never ending pendulum is you have to be in a vacuum with gravity there still, right? Because it
Yeah.
doesn't work without gravity, so it wouldn't work in space.
You want to know what you'd have a never-ending one? Would be like if this was a proton, and there was another proton over here, and another proton over here, and it just oscillated back and forth indefinitely in space. That would be something like that. But realistically, you're never going to get that.
Because it wouldn't work in space because there's no gravity there.
actually.
Correct. You need gravity to actually pull it, so it wouldn't work in that sense. But if you had something where you had two electric plates, both positively charged, and a proton in the middle, and the proton started oscillating back and forth, it would go on forever as long as it didn't contact the plates and there were no air resistance. Good question, Max.
Is air the only wave that like affects like air? Or sound, sorry, sound waves. Are they the only kind of waves that like
That need air? No. So a lot of different waves, so any mechanical type of wave needs a medium. And other types of waves are mechanical as
so
well.
then what's the medium for like light?
There is no medium. Light does not need a medium
Is
to
that
travel.
the only one that doesn't need a medium?
I think all EM waves, all electromagnetic waves, ultraviolet, anything like that, these are all types of EM waves on the EM spectrum. Those do not need a medium, which is why we get UV rays from the sun.
Is
It's
that
hitting
like
the earth.
Wi-Fi or what's Wi-Fi?
I don't know. That's a great question. It's definitely an EM wave of some sort. Yeah, it is, but I don't know enough about it to answer. Wait, what's Wi-Fi? Check.
Can you make like a true perpetual motion machine?
No, it's impossible.
Like, cause I've seen
You
like
try
different
forever.
attempts
It's
of
impossible.
it, but like people get close.
Yeah,
and
but
it's
there's always
like-
energy loss. So what they use, so that was actually, you guys know Riley, right, Teeter? So Riley's science club project last year was to build a closest apparatus to a perpetual motion machine. There it is, right here. And what he did was, he used what are called bearings. If you guys have ever been a roller skater or a ice or a roller blader, bearings have very little friction. So these are two bearings. And what he did is he 3D printed this whole thing. And then he connected a wheel. I'll show you guys the wheel. It got really messy, so it broke and stuff, so he used some hot glue to fix it. The wheel was sitting in the middle, the bearings were connected to an axle. And what happened was he put a marble in all these spots. And as this marble fell forward, it would cause it to move. Then the next marble would fall forward, causing it to move. But eventually it stopped after like 10 rotations because all the marbles would be in a place where it would be balanced. So as it was rotating, there was energy loss between the actual axle that was spinning and the bearings themselves. But a very little amount of energy loss, which allows for the thing to go for a longer time period than what you would normally expect. Does that make sense what I'm answering with? Yeah? All right, let's keep going with this. So this is the general pendulum problem, so you guys have an idea of how that works. What can we do with this? Now, let's continue. I want to see one that actually involves it, that's why. Sorry. All right, let's take a look at... I'm trying to find something that has a pendulum-like problem. This is very much like the problem I did last year, actually. This one, it's not the problem I wanted anyway. All right, here we go. Page 207, number 57. Okay? This says the following. A block slides along a track from one level to a higher level after passing through an intermediate valley. So the image given is the following. Block. Beginning of track, valley, ending higher up. The change in height is denoted as h. The distance it travels along a friction-filled surface is denoted as d. Okay. So it says the track is frictionless until the block reaches the higher level. There is frictional force, a frictional force stops the block in a distance denoted as d. The block's initial speed is v0, and v0 is in this direction. And we're told that v0 is 6 meters per second. We are also told that h in the diagram is 1.1 meters. And finally, that mu in this problem during the track part where there is friction is 0.6.
This is just the opposite
well, in the water slide problem, we ignored kinetic altogether, right? Remember, we didn't even account for it. We have to account for it here, though. We gotta do that. So let's do this. So Tristan, you step us through. In the beginning, it's all kinetic in the beginning. So let's sum of the energy. Sum of the I'm putting E twice. Energy initially equals sum of the energy at the end. So in the very beginning, it is definitely all kinetic. Why is it not potential in the beginning? Because it looks like it starts at a height, right? Chip, what are you thinking?
Because it has an initial velocity.
You could have potential and kinetic in the beginning, Chip.
Are we saying none?
Why are we not calling it potential in the beginning at all? Because it looks like it's at a height above the bottom of the valley, doesn't it?
Maybe because it's right at the edge, like as it's going.
Close, Matt.
Because the reference thing is like at this place where it starts.
So we in this problem need to call where it starts ground level. Why though? You still haven't answered that part. Why?
Because where it ends is higher than ground.
Where it ends is higher than where it started. So we can consider where it started to be the ground. There's one more part you gotta answer still. Nobody's picked up yet. When it goes down, it comes back up to where it started. Those cancel out because it's frictionless. But what else about the problem would we need to know if we consider this to be ground level? What else would we have to know? Technically, we don't need to know because it'll cancel, but what should we really know?
The distance.
Yeah, we're not given the depth of this bowl, right? Of this little valley, of this half pipe. So because we're not given that depth, it doesn't make sense to call that bottom ground level. Now, we could do it. We could absolutely call the bottom ground level, and it would lose H, and then it would gain H, or call it Y0, whatever you want to call it. But I don't want to deal with that. So instead, I'm going to call this my potential energy reference line here. Okay, I'm going to call that my potential energy reference line. And I'm writing PE after I just said U. Sorry. U or PE. Your book, I've always used PE, but your book uses U. And I think your formula sheet for AP uses U as well. So I'm going to start to try to be more consistent there. Okay, so U due to gravity is 0 there. All right, so we've got kinetic in the beginning. And then, at the end, the object ends up above where it started. It ends up above where it started. So what energy does it gain at the end of the problem? Potential. It's got to have potential at the end. Now, here's a question for you. Before it reaches the friction-filled straightaway, what other type of energy does it have? Before it reaches, right before it hits that friction area, D, what other type of energy does it still have? Kinetic. Again, if I ended the problem, if we said that this problem ends right here, and we need to find out the velocity at this instant, we could do it. We could say plus k right here, and then find out the velocity. But the problem doesn't end here. The problem ends here, where it eventually stops. And when it stops here, it no longer has kinetic. Why did it lose kinetic? Why did it lose kinetic?
Because it's an opposing force, which is friction.
Very good. Because of an opposing force known as friction. So I could say at the end, it is also ethermal. And I always do this if it helps. Okay? And if you had me last year, see, I used to call this Q loss last year, if that rings a bell. And I put absolute value around it. Because I think to myself, well, it had a lot of energy in the beginning. Some of that energy turns into potential, but it still has kinetic. But then the kinetic that's left over gets lost due to thermal energy.
How come that thermal energy cancels out kinetic energy?
Because what does it eventually do?
Slow it down and stop.
So where does all that kinetic go that it would have had?
Into the thermal.
Because the thermal energy, remember, Matt, it only starts right here. Where that red dot is where thermal energy begins. So at that moment, although it did gain some height, it would still be moving. And because it stops through the thermal energy, that's where the kinetic goes to. So I know that it's going to stop at the very end of the problem, so I don't have to worry about there being kinetic energy because it's all been lost at the thermal energy.
Oh, okay. Does it say it stops at the end of it?
Yeah, it says, sorry. The block's initial speed is 6, the height difference is 1.1, blah, blah, blah. Sorry, it's earlier on. The track is frictionless until the block reaches a height at a higher level. There is a frictional force that stops the block in a distance d.
Okay.
Stops the block in some distance d.
I was thinking, like, why would you just assume that it, like,
Yeah. If it had velocity still at the end of that, then you would still have. Yep. Okay, so we've got 1/2 mv squared equals. Now, for v, it's really v0. It's the initial velocity. So you can put v0 if it helps you. But if it's on the left-hand side of the equation, it's initial. If it's on the right-hand side of the equation, it's final. And this is going to equal mg. I have a tendency to use a y. The book here is using h, so I'm going to use h. But mgy, mgh, no difference, right? H is your height, y is your y value, your height. And then plus your thermal energy. And our goal is to determine the value of D. So again, let's make a really important conclusion here. Any time that you're finding out the value of D, the portion of the track that involves friction, you either have to have a flat area there so that Fn is equal to Fg, like we did in the last problem, or you have to be given the friction force. Are we given the actual friction force? Do you see anything here that tells me Ff in the problem? You know mu. But are you given the friction force? Explicitly, no. So if you have mu, what do you have to multiply mu by to get the friction force? Fn, which is mg. Why is Fn mg? Because it's on a flat surface. So again, if this problem involved friction along the curved path, you cannot use mu mg for Ff anymore. Because Fn changes. Fn is this, then Fn is this, then Fn is this, then Fn is this. So Fn would be varying along that entire surface.
They would have to give you FF. Right?
They would have to tell you that Ff as an average is this value. Yep, absolutely. Now, again, for this problem, it's not the scenario, so I'm not concerned with that. So we're looking for D. I'm going to replace FF with mu mg. And there's our answer. So who said it's like the same thing? Yeah, Tristan, that was you, right? It really is, right? I mean, look at the answer. This was L before. We still divided by mu mg earlier. This just changed up a little bit, right? In the first problem, we started with potential, and then we started with elastic. In this problem, we start with kinetic. We gain potential, so that shows as a minus here, because we're losing some of our energy to potential, and then some of our energy we're losing to thermal. So it looks very similar as a generic solution, but there are some differences. Okay, again, kinetic is what you started with, whereas here, you ended with potential. In the last problem, you started with potential, and you started with elastic. So this was positive in the last example, not negative. And elastic was also positive, because you started with both. Here you start with kinetic, which is why it's only positive here. Okay? This is losing energy to potential, and this is your division to solve for D. Chip.
Is the only way you can gain potential energy from the beginning is with an initial velocity?
Or, there's one more.
Elastic energy?
Or, another one. Elastic's right too, yeah. Work done by an outside force.
Oh, yeah.
So if work is done in the vertical direction by an outside force, it causes you to gain potential energy, because the work done equals the change in energy. So work done, kinetic energy or elastic energy will give you potential energy, will allow you to gain potential. When you walk up the steps to Loyola, you are doing work every step, right? You're literally doing work. When a pump pushes water up here, it is electrical work. It's the electricity that you're literally using, and that is what's creating a pressure differential, which causes water to flow out of here. But it's still work being done by a turbine, by the motor, by the pump itself. There's a problem, I think I signed it for your homework yet. Chapter 7, I assigned you guys your problem. I just put the problem set for chapter 7 today, actually, about an hour ago. But for chapter 7 problem set, I gave you a problem that talks about how much work is done by the motor of an elevator. How much work? And the idea is that, well, the amount of potential energy it gains is really the work done by the motor. right? The motor itself has to give you the energy to gain potential there. So it asks you that kind of a problem. Now, elevators, though, have also a counterweight that pulls down. That counterweight also gives you potential energy because it's lowering its potential energy, so the elevator is gaining. Have you ever seen that before? An elevator has a counterweight on it. There's a whole theory behind elevators that even if the motor stopped working, the counterweight should prevent it from falling and going down to the ground. So even if you didn't have the motor working with you, the counterweight is enough to balance the elevator at any given moment, or it's supposed to be at least. You know that's not true, by the way, because you guys saw that incident, right, recently?
Oh,
Ooh.
did you show it to us?
I think I showed it to a couple of guys. The guy gets crushed, yeah.
What happened?
The guy gets pulled into an elevator shaft and crushed to death. And there's a video of it. It's like,
Wasn't it like that the safety rating in elevators is always like 11 times lower than the actual?
the factor of safety is like 11 or 20, or something crazy like that. Because of the fact that it's an elevator.
Don't the police have counterweights to assist with the lifting of it?
Yep, absolutely. That's why when you see things like when they're lifting a piano up to a building to put it into a window, they have several different pulleys to actually decrease the force needed, but you pull it over a longer distance and there's a counterweight on the end of it. There's a show I used to watch as a kid, and it's really, when I look back on it nowadays, I look at this show and I'm like, Jesus, some of this shit was really messed up. And it was called Home Improvement. Has anyone ever heard of that?
That show they tear down.
Home Improvement?
Is
The show was called Tool Time, that the guy is on. It's Tim Allen is a comedian. You know Tim Allen?
yeah.
Okay, he's a comedian on the show called Home Improvement, but he's really he's like a Bob Vila. You know Bob Vila? Home Improvement? So he does all like, if you want to fix your house up around the house. So the show he runs is called Tool Time, and it teaches people how to use tools. Anyway, the point is though, I watched an episode like 3 days ago, I remember it, that he creates a pulley system to help his son fly as Peter Pan in the play. Because he keeps saying to his dad, he's like, Dad, I want to fly. And the guy who does the play doesn't know how to create a system for this. He goes, so you need power? I can give you power. Let me develop this. So he develops like a pulley system, and to test it, he has his kids be the counterweight on the end. And he harnesses himself in, and they pull him up to like a certain elevation in the window, and like he's like next to his house and talking to his wife, and the ice cream truck comes around the corner. So what do you think happens? The kids. What do you think happens? The counterweight is the kids.
The kids like
The kids let go, they run for the ice cream truck, and he drops and falls. Yeah. The kids. It's not really obviously happening. It's it's TV. Anyway, the show is really good when it comes to like tools and like lifelong lessons and morals. But when you look back on it, it's kind of messed up actually. I don't want to get into politics right now, but let's just say I don't agree with the politics of the show. That's all I'm going to say. All right, so the next example. Let's do one more. Yeah, we have a little time. Okay. We're not going to get into politics right now because that's going to get messy and we're going to all disagree or maybe we disagree. I don't know. But I don't disagree.
What?
All right, number 93, page 210. Okay, page 210, number 93. Here's what it says. A playground slide is in the form of an arc of a circle that has a radius of 12 meters. Beginning, ending. It says the maximum height of the slide is 4 meters. Or the starting height, I should say, is 4 meters. And the ground is tangent to the circle. So that's good, we drew it properly. The ground is tangent to the circle. A 25 kilogram child starts from rest at the top of the slide and has a speed of 6.2 meters per second at the end. What is the length of the slide? What is the length of the slide? Again, the child starts at 4 meters, ends with a velocity of 6.2 meters per second. what is the length of the slide? It goes on to say, what average friction force acts on the child over this length? If instead of the ground, a vertical line to the top of the slide is tangent to the ground, what are the length? Okay, so that's what we're going for, those two things. So first it says, what is the length of the slide? So how are we going to figure out the length of the slide?
You find the circumference.
And then divide it by 4. So the first part is the easier part. The length traveled here is a quarter circle. It's really important that we see that. Look, I'm going to highlight it in green. There's the length of the slide that we're talking about. It's a quarter of a circle. And we know the radius for that reason. So right off the bat, part A asks us, find the length of the slide L. So we could say, well, it's really just 2 pi r, which is circumference, right? L equals circumference divided by 4, because it's a quarter of a circle. So that'll be 6 pi. Should be 6 pi, right? Yeah, 24 over 4 is 6. So that's the first part of the problem. And that's the part that is like, I don't know, that's not really AP physics at all. That's just physics. The second part of the problem says, determine the average friction force. Determine the average friction force while sliding on this length of slide, of the slide. Give me a step process through it. Go ahead, Chip.
Well, I was thinking you could do like delta K equals force times distance.
Delta K. There's a problem there. Kinetic is not the only energy present. If it were on the ground, you could do that. And that's the work kinetic energy theorem you just stated. Right? The work kinetic energy theorem tells us that the delta K equals the work done by friction, by anything, right? But K is not the only energy present. So instead of using the work kinetic energy theorem, which is useful when things are only on a flat surface, we're not going to use that. We're going to use the conservation of energy formula instead. So can you tell me what kind of energy we have at the beginning?
Only potential.
Only potential in the beginning.
And at the very end, you only have kinetic.
And at the what?
At the end, you only have kinetic.
Careful.
Thermal.
Yeah, thermal's got to play a role somewhere here, right? It tells us already, find the average friction force. So here's the thing, watch. Let me give you a little hint before we even do it. If you calculate this and calculate this, they're not going to be equal. You're going to have a discrepancy. That discrepancy is work done by friction. So if you have 30 joules of potential to start and only 20 joules of kinetic to end, you're missing 10 joules, right? That's the work done by friction over here that you're missing. Try it. Calculate it. You got all the numbers. 4 is the height to start. Mass is 25. 4 times 25 times 9.8 is 980. So this number here for you is going to equal 980. Then if I get the kinetic energy here, the kinetic energy is going to be 1/2 mv squared. I can't do that in my head, sorry. 1/2 times 25 times 6.2 squared. 1/2 times 25 times 6.2 squared. Just want to get a number so you can see the discrepancy. You got it ready? Ah.
At 480.5.
480.5? So where's the question mark? What does that mean? It means this. It had potential in the beginning. It lost a bunch of it, so it only has this much kinetic at the end. We're considering the ending point to be ground level, so there's no potential at the end of that. So the question mark is really thermal energy. The question mark is really thermal energy. So let's replace that with E thermal. And this is going to be friction times the path taken. Remember, the path taken is the physical curved path. It is not the direct hypotenuse. Okay? It is not a direct line. It is not the height of 4. This L is 6 pi. It is the length of the slide. It is the length of the arc taken by this person sliding. Chris. Hagen? How did I get K? Kinetic energy, 1/2 mv squared. Yep. I didn't put them in here, sorry. mgh equals 1/2 mv squared at the end plus the thermal energy. I'll put work done by friction there. I'm squeezing those in, sorry. mgh in the beginning equals at the end 1/2 mv squared plus the work done by friction. WF, work done by friction. Yeah.
Like in the case of, let's say you're spinning like a weight in a horizontal
Mhm.
plane, are you constantly doing work on it?
Are you constantly doing work on it?
Because it has an acceleration, the velocity is never constant. It would be speed that's constant if it's a.
The force you apply, though, when it's in circular motion is a centripetal force. It's acting toward the center of the circle. And the position vector is always tangent to the circle. So the cosine would be the cosine of 90 degrees, which is 0 there. So I don't think you're doing work at that point, actually. That's a great question. I haven't thought about it. Let me think about it a little more. Yeah. So solve for FF, please. Solve for FF. Power of 6 pi. Solve for the average force of friction. So listen carefully, please, okay? You have Chapter 7 homework. You know that already. I highly recommend that you do Chapter 8 multiple choice. Highly recommend. I already made that an assignment. I want to give you your quizzes back. So I curved your quizzes slightly, only because almost everybody got the first problem wrong. Remember the first problem? Most of you chose the right answer. Most of you chose choice E because it went up by a factor of 4, but it said, what is the difference? So when something goes up by a factor of 4, it means that it's 400% of what it was. If it was 100% in the beginning, and it goes up to 400%, what's that difference actually? 300%. Like 9 out of 10, or 9 out of 10, however many of you chose 400% as your answer when it was 300%. So relook at number 1. So I threw everybody a 1.5. So you could add a 1.5 to your score. Okay, to the numerator, you could add a 1.5. The other half, I was just being nuts. I did not put these on your grade online yet. There's no grades online right now. I think I'm going to wait until I give you the first test to put your grade online and to also include Lab 9, which you already turned in. Don't forget, please, Lab 10 that you guys worked on today. Real quick, Lab 10 that you worked on today with Alex, you're going to present it next week. I already put a due date of when you're going to present. So if you want to present with a PowerPoint, if you want to show a video, if you want to do math on the board while you're presenting, each group, listen, each group, 20 minutes max. So you need to make your presentation fit 20 minutes of that period. Is that clear? Okay, if anything, actually, no, 15 minutes, because we're going to need a little extra time at the end to talk. So 15 minutes max for your presentation of your lab. The 3 of you figure it out. There is one group of 4, Spencer and Max, you're both in the same group because you were not here. So that one group of 4 has 4 people. But 15 minutes max presentation at conservation of energy. So I started just writing this. We already went over the left side the other day. We talked about the fact that the change in an object's potential energy is equal to the negative work done. And I gave the example of the elevator, and that's the best example. As the elevator gains potential energy, how does that happen? It's because gravity, right? Gravity really is doing negative work on it the entire time. It's moving up, gravity is pulling down. So the work done, or the negative work done by gravity, ends up being equivalent to the amount of potential energy that is gained. So this concept here, right there, is what really tells us about this concept right here. Because what is work by definition? Work is also the integral of force. We talked about how work is force times distance, but when the force function is not constant, we replace work with this integral. So this W is replaced with this entire expression. And that should look familiar because we've already stated that a couple times. Again, work is force times distance. But when we don't know the work or the constant force, or if we don't know if the force is constant the whole time in general, we have to use a function for force because it can vary now. And this is true for a one-dimensional force. So, as a result of this, we want to make a couple statements. And these statements are going to allow us to do a good job of reading what are called potential energy graphs, which is part of the AP exam. So as a result of this, what we can say, if the change in potential energy is equal to the negative integral of work, of force here, then what we'll end up getting is that force, f of x, is going to be equal to the negative derivative of potential energy with respect to position. And these two things are just pretty much opposites of each other. Again, the integral of force gives you potential energy, so the derivative of potential energy gives you the force. And remember that these are negative quantities here. So when we look at this and we start to think, well, what are we going to really need from a potential energy graph? What we're going to recognize is that if we're given a potential energy curve, we can take its derivative at any value of x at any position and figure out what the force is from the derivative of the position. And that position really comes from the gravitational potential energy. But in general, we're talking about just potential energy. So this key right here is where we're going to use. So I'm going to give you a couple of graphs in the next few slides. I'm going to throw a couple of graphs up, and we're going to go into a little bit of detail about how to read these graphs as far as how you're going to need them to answer questions on the exam. Specifically, you're going to see these types of questions show up most likely in a multiple choice type problem. If they were a part 2, it would be only a small portion of a part 2 or a free response. So let's together look at a couple examples of graphs of these. The graphs I'm about to put up on the board, you could sketch if you want, but they're also in your text. So it's on page 189. Okay, on page 189. So let me go some of these graphs up so you can see them first. So let's start with this one here. Okay, and let's take a look at the top two first. So we're going to look at part A and B, or the graphs for A and B first only. So only A and B to start this. So let's start by looking at graph A. For graph A, we're seeing a potential energy graph. We can tell because the y-axis is labeled as U and the x-axis is labeled as position. So this is the potential energy of an object as a function of its position. That's what we're looking at right now. And the first thing that we're going to recognize is that this function varies. It changes over, or changes as a function of the position itself. And what we'll notice for this is that the corresponding force graph is drawn on the far right. So let's make sense of this to make it clear. So first, what is the slope of the graph of the potential energy in the very beginning? What is the slope in this region right here? 0. So we notice the force is a value of 0 to start. Okay, the force is a value of 0 to start. Then what do we notice is that the slope is suddenly very, very negative, right? And what happens is it goes from being somewhat negative to more negative to even more negative as we think about the tangent line. And I can draw that so we can see it, right? The tangent line is somewhat negative, then more negative, then more negative until it's pretty much a constant tangent line slope in this region right here. So the slope is getting greater, but in the negative direction. And because by definition, force equals the negative derivative of the potential energy function, we could say that our force is really, again, the slope at that point or in that region. Well, the slope here is very negative, right? We just said it's very negative, and yet the force is very positive. And that comes from the fact that we have this negative sign here. So the force responsible, or the force felt, we should say, by this object moving as a function of position x, that force spikes up until it becomes a maximum at x1. Until it becomes a maximum at x1. And then it starts to teeter off. And then what would the force at x2 be? What would the force value at x2 be equal to?
0.
Why 0?
Because the tangent line is horizontal.
Yeah, that's a horizontal tangent right there at x2. So if I were to draw the tangent line in at x2, it means that the force at x2 is equal to 0. Well, there it is on the force graph. That's the force at x2, right there. Right? So what happens is we notice is that, again, and maybe I can I erase any of this? I can erase part of it. So what we'll notice here is this. The slope gets more negative, more negative, more negative, more negative. Now it's constantly negative for a little while. And then here, it starts to turn around. The slope becomes more positive, more positive, more positive, and then the slope is 0. And then the slope becomes positive for a while. And then negative, or less positive, less positive, less positive, 0 slope. and then negative slope. Just like in calculus, the same way you analyze graphs and found maxes and mins and turning points, is the same way we're applying this to forces, except the key is that we have the negative here. So all of those quantities are going to be the opposite of the actual slope. So because this slope was becoming more and more and more negative up until here, the force became more and more positive. Then the slope became less and less and less negative until it became 0. The force becomes less and less and less positive until it becomes 0. And then at x2, we see the slope is becoming larger until the slope reaches a max. Well, this value is going to become more and more negative until it reaches a min, or a max, but in the negative direction. So this peak right here, this corresponds, right, this spot right here, to this point right here. What do we call this in calculus? The point where we go from this kind of curvature to this kind of curvature. What do we call this point right here? What is it called, Anne? What is it? A point of inflection. A point of inflection. And for a point of inflection, what do you know? A point of inflection means that the second derivative is equal to 0. Well, isn't this right here the first derivative? The force is equal to the first derivative. Well, what's the derivative of the first derivative? That's the second derivative. And you'll notice right here, what is the slope of this line? The slope of the derivative is the second derivative, and it's 0 at this location, which again is why this is representing this value here corresponding to this value here. I might actually, you know what I'm going to do? I'm going to superimpose for a second. Hold on. Let me make this a little bit better so you can see them lined up. How could I do this? Here we go. I'm just inserting an image, guys. Sorry, give me a sec. Let me just crop it down so it'll work. I want this to work nicely. There we go. Okay. So for the sake of right now, here's what I'd like you to do. Ignore, actually, I'll just put a block over it to make it easier. Oops, I don't want a circle. So ignore the graphs on the far right there for now, because they're not really helping us with much of this. Let me just put this over it to make it easier. There we go. Okay, ignore those graphs on the right. So what I did is I took the graph that was on the top right, put it down here so we can line it up. This will make life a lot easier. You've done this method in calculus, right, where you line up the derivative directly below the original so that you can see where the maxes and mins correspond to the zeros. So that's why I'm doing it this way. So again, the value we want to consider is that the graph on the top is like the original. The graph here is the negative derivative. The negative derivative of the original at the top there. So where we have a slope of 0, we go down, straight down, and that corresponds to a value of 0 for the derivative. But this is the one I was just talking about. I'll use blue for this one. This is the spot I was referring to right here. So if I go straight up with this one, I know that that is my inflection point of my original. Right there is the inflection point of the original and yielding the max of the derivative. And it's the max, but on the negative side, which again, we're going to call the minimum value, but it's one of our extrema. That's all that matters, that this is an extrema, because again, this slope is 0. But the slope of this guy is really the second derivative, right? That slope equals 0, which tells me that the second derivative of the potential function is equal to 0 in this case. Okay, the second derivative. Because it's really the first derivative of the first derivative, which is the second derivative. Then if we continue to go, what we'll notice is that the same corresponding thing happens over and over. We'll notice that whenever we have a max of one of these, we go straight down, we'll have a 0 of one of these. Whenever we have a max of one of these, we go straight up, we'll see we have another inflection point. Again, a min here creates a 0 at x4. A max in this graph is where the inflection point occurs again. We go from positive concavity to negative concavity. And then at the very end, we'll see a flat line. And a flat line needs a slope of 0. And when this slope is 0 right here, this must also be 0 right here on the right. So the first graph I want you to or the first set of graphs, I want you to recognize, again, that the negative derivative of your potential function will give you the force that it feels at that location. And notice I'm saying at that location, and I'm not saying at that time. Because I don't know anything about time right now. I know time is elapsing, obviously, as we apply force and change that force that's applied. Time is definitely elapsing. But now I'm not plotting this F, or I'm not plotting this, this force here, F as a function of time. I'm plotting it as a function of distance. So I'm really looking at the position of the particle or the object as we continue to go. Let's look at the second two graphs, which are probably a little more helpful when it comes to studying for the exam. So let's look at these next two here. And the next two are going to be graphs C and D on the same page. Graphs C and D. I'll just crop it so it works for us. There they are. Okay. So let's take a look at these two graphs now. For these two graphs, here's what we want to start focusing on actually. In these problems, we are given the total mechanical energy in the system. Total mechanical energy in the system. And in both of these scenarios, that value is 5 joules. But the potential energy varies. The potential energy varies. So what the graph on the right is trying to show you is that deviation, that gap, the margin here, this margin, is the kinetic energy. Why? Why is that equal to the kinetic energy?
Because if you subtract the potential energy from the total energy, you'll have the kinetic energy.
Yeah, because why? The total energy is kinetic plus potential, and that equals a constant. This is conservation of energy. Now, obviously, what is the assumption we're making here? There's no what?
Non-conservation,
There are no
conservative forces.
Yeah, good. These are all conservative forces. Very good. There are no non-conservative forces in this problem. There's no what? What are we talking about? What's the non-conservative force?
Friction.
Yeah. There's no thermal energy loss due to friction here. So as a result, we know that the gap between the total energy line and the potential energy line is always going to yield how much kinetic energy we have. Okay? And again, this constant is really E mechanical. That's what it really is. The total energy or the total mechanical energy in the system. In the system. Now let's make a couple points out, or let's mark a couple points here and let's take a look at some things. First, when the potential energy equals the total energy, what can we conclude? When the potential energy equals the total energy. Chip, what are you thinking?
There's no movement occurring
There's no movement occurring. Very good. How come, Chip?
because potential energy is just mgy, and so there's no velocity within that. So, sorry, I'm trying to explain myself better. I'm just a little tired.
That's okay. So you're right. You're totally right. At this location that Chip is referring to, right here I'm pointing to, when the potential energy is equal to the total energy, why is there no motion? He's right. There's no motion. But give me a better explanation as to why.
Because there's no kinetic energy and the mass can't be zero, otherwise there'd be no potential energy, so V has to be zero.
Yeah. Let's look at this. If this total energy is 5 and the potential energy is 5, then the kinetic must become what? If this is 5 and this is 5, then this must be 0. And if there's 0 kinetic energy, there must be 0 velocity. So on these graphs, maybe label this right here, call this a turning point. A turning point. Remember, we're referring to one-dimensional forces being applied. So this is an object literally oscillating left to right or up and down. It's an object oscillating left to right or up and down, but it's not doing both of these. So at this instant, the object has no velocity because it has no kinetic energy, and therefore at this instant, the object must turn around. It must turn around. Yes? How do we know it must turn around? Well, let's think about this. If the potential is 6, right, and the total is 5, how is that possible? What must the kinetic energy be in the beginning?
You must be moving in the negative direction.
It must be considered to be like a negative or moving in the negative direction. And then here, if I have a total energy of 5 and only a potential energy of 3, now I've got a positive kinetic energy gap. That's a positive gap of 2. So the kinetic energy goes from being like a negative quantity because we've got more potential than we do total. So the kinetic must be negative in this region. And then anywhere beyond that, the kinetic energy is positive in all of these regions. So you go from negative kinetic energy, which is like moving this way, to positive, which is like moving this way. Yeah, sure.
Kind of like a quick deviation, but when you have a spring
Uh-huh.
that's oscillating, the point at which there's no potential energy, is that when it's in between the two oscillating points, because you're like the equation's like negative kx, so when you put 0 in for x. Okay.
The endpoints when a spring oscillates back and forth is when it has maximum potential energy. When it has no kinetic energy, it's at the endpoints also, because it stops at the endpoints. Those are the turning points. When it's crossing the middle where the equilibrium is, that's when it's got no potential because the spring isn't stretched, so it can't have potential. And because it's moving, it's got the most kinetic energy at that moment. So at the ends, we've got maximum potential, minimum kinetic. In the middle, we've got maximum kinetic, minimum potential. They're opposites of each other. And that's the concept we're getting at here, right? That if this goes up, this must go down. If this goes down, this must go up. They have to sum up to give you some constant. And that's what conservation of energy tells us. When could we say the object is moving fastest on this graph? When might we say the object is moving fastest on this graph? At what x position might you call it? Where it's moving as fast as it can. As fast as it can. Think about when I say the word fast, what am I referring to? What kind of energy? That's how you have to deduce your answer. What kind of energy is speed a function of? Or what kind of energy is a function of speed? Karen? Kinetic. So do you know the specific location where we have the most?
Would it be x2?
It would be. Very good. x2. Well done. So x2 is where there's the biggest gap between the total energy in the system, which is 5, and the potential energy at this point, which is 0, it turns out. So at x2, it's all kinetic energy. The kinetic energy is 5 at x2. At x2. So because kinetic energy is a maximum at x2, so must the speed of this particle be at x2, a maximum. And we already said when kinetic energy is 0, that's at this turning point right here. Right? At this turning point right here. How about this? When is the kinetic energy a constant? When is the kinetic energy a constant? And I'll accept multiple answers. Not done. At x5, okay, and give me more than that, Chris. When else? When else is it a constant? I want a duration of it. So,
x5, x10.
very good. All of this is the same gap, isn't it? This is the delta right here. This is the amount of kinetic energy in the system. Total minus potential. So if the gap isn't changing, it means that the kinetic energy in this region from here onward is a constant. Chip?
0 to x1.
Very good. Also in the very beginning, it's actually not till x1, Chip. It's till this mark right here, which is kind of off.
Oh,
It's up
okay,
until that.
so
Yeah. It's that other mark.
Before x1.
So before x1, from here to here, this gap isn't changing, and then it starts to curl, right? So up until this location right here, the kinetic energy is also a constant. Well, think about it logically. The regions you just gave me answers of are when the potential is a constant also, right? If the potential is constant, it means it's not changing, and therefore the kinetic can't be changing. So wherever the potential energy function is constant, so must be the kinetic energy of the system. Max.
If you extended the graph leftward and it were negative x1, negative x2, etc., how would the graph change? Or,
I don't know. It would have to be given to you.
yeah.
I'm confused.
Like if
Yeah.
because then the potential energy right now it's 6.
Uh-huh.
If you kept that line,
Uh-huh.
but then would it become negative 6?
And kept going like this, Max? Like in that direction?
Yeah.
Well, the potential would still be positive 6. Your position would just be negative relative to where you started. Remember, this is your position here on the x-axis. That's what's becoming negative, right? When you cross over. Your potential energy is still up at 6, if it were still at 6, like you're saying. Then the potential energy would still be a positive value there.
And what about the kinetic energy?
The kinetic energy, if the total energy was constant, which it is here, the kinetic energy would still be constant also.
There'd just be stuff going on that we don't know.
Correct. We don't know what's happening at that point. But it would be just a negative position on the other side of your starting point. Okay. I want to add in a couple more things. Let me think. Do I want to add that in actually right now? No, I'm going to hold off on that. All right. Your book gives a good question. We're going to do it. It is on page 190 to 191. Okay, so let me put the figure and the question up on the screen so you guys can see it. I'm going to import a couple of these. I'll start with the question. I'll add another question to it. And there's a part B to it also. Hang on. I missed part B somewhere in there.
It's my hustle juice. I have a coffee mug and it says hustle juice on it. It's so great.
Wonder where that came from just now. This is on page 190 to 191. Okay? All right. So let's get into this problem. So it says a particle moves along an x-axis in a one-dimensional motion while a conservative force along that axis acts on it. Conservative force. We're talking about the potential energy here on the graph. The potential energy is associated, or that's associated with this force, is plotted in the figure to the right. That is, if the particle were placed at any position between x equals 0 and x equals 7, it would have the plotted value of u given. At x equals 6.5, the particle has a given velocity. And the I just stands for, again, x direction. Part A says, from the figure, determine the particle's speed at x equals 4.5 meters. At x equals 4.5 meters. So what kind of an approach can we take here? How might we start a problem like this? What do we want to think of for a starting point? Max, give me a starting point.
I would write 1/2 mv squared plus mgy equals 16.
1/2 mv squared, go ahead, plus mgy equals
16.
how come?
Because that's the total mechanical energy.
Total mechanical energy is 16. That is a constant, and that is always going to equal the potential plus kinetic. So that's a great starting point. I like that. So part A says we want the speed at 4.5 meters. At 4.5 meters, we want the speed there. And we're given something about the speed later on, I think, right? We're given something about the speed later on. We're also given something about the mass of the particle. So what might we have to do to figure out part A? What are you thinking? Again.
You should do 16 minus 7 equals 1/2 mv squared.
And what's the 7 coming from?
That's when the potential energy is equal to 7 joules. But since you want your kinetic energy, you're subtracting from the total mechanical energy.
Very good. So this is 7, this value here. And that is the potential energy. And here is the kinetic energy. So although we're writing mgy, as Max said, this problem doesn't actually give us anything about a change in height, right? So we're going to notice whenever we're given these graphs, these potential energy graphs, we're probably not actually going to be using a delta y in these problems. Does that make sense? We're most likely not going to use a delta y because the graph is giving us the overall potential energy, so we're replacing that entire expression. Again, because the governing equation we started with was this. Kinetic plus potential equals total. Kinetic plus potential equals total. And the potential in this case is 7. It is 7. So that sounds like a good approach to take. And then we're looking for, again, the particle's velocity at that moment. Or speed, rather. Sorry. Speed at that moment of when x1 is 4.5. So let's take a look a little bit further here. We could say, well, you know what? We're given the mass in the problem. It's a 2 kilogram particle. So we know that quantity. So this is just going to be a 1/2 times a 2, which is really just a 1. So that doesn't matter. And then it's just v squared. So it's v squared plus 7 equals 16. Or v squared equals 9. And therefore v equals 3. Again, it's 1/2 times 2, so that doesn't actually do anything. It's a 1. So move the 7 over and take the square root. So the speed of the particle at a position of x equals 4.5 meters is 3 meters per second. Okay, the speed itself is 3 meters per second. And again, where are we in the graph? We're right here. That's where we're on the graph, at K1. Okay, at K1. How about part B? How about part B? Where is the particle's turning point located? And I want not only the answer, but I want you to answer with the following and say why, or explain why you give me the answer you give me. So where is the particle's turning point located? What are we thinking here? What are we thinking? Just Max? You got the last one. Somebody else get this one. Where is the turning point? Turning point, turning point, turning point. Let's use deductive reasoning. Turning point means, am I moving? Am I moving at a turning point? He's like, I don't know if I should answer this because it feels like a trick question. It's not a trick question. You're not moving at a turning point. Yeah, you're going this way, right? And then to turn around, you have to stop and then turn back around, right? So at a turning point, you're not moving. If you're not moving, you don't have what? Kinetic energy. When you don't have kinetic energy, all the energy must be. If all the energy is potential, the potential must equal the total. So it's really a deductive reasoning, same way we did with the other graph. So what would our answer be for this one?
It doesn't have a number. It just, yeah.
Oh yeah, you're right, it doesn't have a number actually. That's a really good point. So where would it be though, right? Where would it be?
Right where it crosses there.
Yeah. Right where it crosses the total amount of energy in the system. Okay, right where it crosses the total energy in the system. Max, go ahead.
Couldn't you solve it exactly by setting energy y equals 16?
Remember, y is not x. They're different things. This is not, this right here, this y max is not the same thing as this x right here. We're talking about the potential energy as a function of the position of the particle. So this y value here is not the same thing as the number that we're looking for there. So we're really trying to just read the graph and utilize the data. So yeah, it's this point right here.
So would you just verbally respond to that, or?
Yeah, so most likely for a multiple choice or question like this, the answer choice can be like between 0 and 1 seconds, between 1 and 4 seconds, between 4 and 5 seconds, at 5 seconds, at 7 seconds. So you'd probably be given a region to choose with an answer. How about part C? Evaluate the force acting on the particle when it is in the, I'm covering up on line, sorry, in the region between 1.9 meters and 4.0 meters. The region between 1.9 and 4.0. What are we thinking about for the force acting there? For the force acting, based on just the concept of the graph. Yeah.
Well,
you have to take the negative integral, but I mean, I guess you'd have to. I mean, it's kind of hard to see where 1.9 is on there, so.
It is tough to see where it is. I agree with that. I agree with Chip that it's really pretty tough to see that. Be careful though, because Chip made one mistake in his statement. He said we have to take the negative integral, right? Force equals, not the negative integral. Go back a couple slides if you need to.
The negative derivative.
The negative derivative. Okay? So this is one of those things that we're going to have to start, getting used to using more often than not. So the force is equal to the negative derivative of your potential function with respect to position. And we want to know what the force is at a location between 1.9 and 4 meters. Why 1.9 and 4 meters? If we look at the region that's listed between 1 and 4 meters, we can see that the slope is not changing in that entire region. Right? The slope isn't changing. I'll highlight it in blue. The slope isn't changing anywhere here. So really, we're looking for the negative value of that slope. So we can calculate it using just the secant or just slope formula. Okay, so we're looking for this guy. So this is going to equal, let's do the slope here. So this is going to be y2, which is 20 minus 7 over 1, and it's the negative of that, 1 minus 4. Okay, I'm using this coordinate. I'll put them in yellow here. I'm using the 2 yellow coordinates to calculate the slope. So 1 comma 20, and 4 comma 7. So this is my delta y, this is my delta x. I'm going to get, what is this, 14 over 3? 14 thirds? 13 thirds, thank you, jeez. And it's negative, right? So it's negative 13 over negative 3, or 13 thirds. And what would my units be for this? What would my units be? Derivative of potential with respect to position. What units would you get? I made it sound tougher than it is by saying. What is it? It's just newtons, good. I saw M was going to say newtons, but then as soon as I said derivative of potential with respect to position, what units, and make you think, oh, that must be tougher. It's just newtons. Because we're solving for a force here. So what does this tell us? It tells us that in that region, there is a force applied, and that force is not changing. The value of that force is around 4 1/3, and it's not changing in that entire region from 1 to 4 along the position axis, from 1 to 4. Okay. That's section 8.3 in your book, by the way, in case you're looking later, section 8.3. And I kind of went back to that because we've been looking at chapter 8 problems, but we didn't really get into anything with potential energy graphs. And when I looked at old AP problems this weekend, I saw that some of them, once in a while, ask you questions based off of a graph of a potential. So you're aware of this concept. This is going to be one of your keys right here. And if I recall, let me see if this is correct. I think part of it is on your formula sheet, or it's given the other way around. Let's see. On your formula sheet, you're given. Let's see. You're given that work equals f integral of f times dr, which is f of x dx. Given the other part, power derivative of work with respect to time. Potential. It's not on here, okay? So maybe jot this concept down right here. Okay, that the position, the potential graph's derivative with respect to position gives us the negative force. Yeah, it's not a formula on there. So one that you might want to add, right? One that you might want to add to your collection of extra formulas that we've come up with. All right. With that said, let's get into a couple more examples from chapter 8. And we get to the end of the period. All right, so here's what I'd like to do. Tonight, I'm going to send you an email, or I'll put it on Moodle. I'm going to give you some practice problems from Chapter 8 that I recommend that you look at. On Thursday, you're definitely going to have 15 minutes per group to present your lab, and I'll probably give you a free response quiz for Chapter 8. So a problem where you're having a spring, some sort of velocity, some sort of height, where you're looking at elastic energy, gravitational potential, and kinetic energy all in one problem. Okay?
Like a non-conservation.
If friction is applied in the problem, then you have to include it. Absolutely.
On the right-hand side of the equation, is that a positive?
For friction?
Yeah.
The easiest way to think about it is this, Chip. Based on where you're going to put friction, you have to think about the energy before and after. If you lose energy, the energy before should be more than the energy after, right? Think about it. If you're losing energy to friction, more in the beginning, less at the end. So if you're going to put it on this side, it's a positive.
Okay.
To account for the missing part. But if you put it on this side, it should be negative. Because you're losing that energy. Does that make sense?
Yeah.
So you can treat it either way. You treat it either way. All right, guys, have a good day. I'll send you that email to update you so you know, but I'll put it on Moodle as well. All right, what I'm going to do is this, to give you guys a little bit of help, because I think the hardest part some of you are having trouble with is just recognizing when to use what types of energy and what instant in what part of the problem. So I'm just going to make up some problems that have ridiculous natures to them, and we're going to look at the types of energies along the way. I'm not going to get into like the math and actually solving, because it's just algebra actually, the math. It's more of the setup that's important right now. So let's look at a problem that says the following. The first one we're going to have is this. An object on a cliff from a spring that lands in a body of water. Hits the water, slows down, and sinks to the bottom. Okay, let's take a look at this example for this one. So, first, whenever an object is compressing a spring and storing energy, it can't be moving. Now, throughout the process of compressing, it is moving. I get it. What I'm saying is, when you compress a spring fully into the loaded position, right? You know what I mean by loaded position? You pull the spring all the way back, and you're waiting, and then you release. The moment you pull it all the way back, it stops. So whenever you have a spring compressed fully, it's not going to have kinetic energy also. Is that clear what I'm saying? So the start of this problem involves gravitational energy and spring energy. Potential due to gravity and potential due to the elasticity of the spring. UG and UE. So that's the beginning of this problem. Now, trust me, I know it's going to have kinetic energy. I get it. So when does it have all of its kinetic energy, though? I should say this. When does it have, before it reaches its max height, when does it have the most kinetic energy? Before it reaches maximum height, let's put max height up here. Before it reaches max height, when does it have the most kinetic energy that it can have? Chris? Right as it leaves the spring. Right as it leaves the spring. And I know the spring does give a little bit of vertical extension also. Right? It does. So we have to consider that. But the idea is that the moment it leaves the spring now, it's got a lot of kinetic energy because that spring energy has caused it to move. And then what is that kinetic energy going to turn into? So let's draw the spring extended. I'm going to use blue. It's going to be tough to draw this, so bear with me. Here's the spring having been extended already. And now here's the object right there. At that moment, it's got kinetic for sure. I agree with Chris. It's got kinetic there as well. It's also got what at that height? It's also got what at that moment? After the spring is completely extended. The spring is completely extended. What else does it still have?
Gravitational and elastic potential energy.
Gravitational, no elastic. The spring is completely extended at this point.
It doesn't have the potential energy backwards.
the mass is released from the spring. And we're talking, yeah, that's a great point. So you know what Matt is thinking about right now? He's thinking, oh, once the spring fires, the spring is going to get pulled back. In a system where the mass is physically attached to the spring and the mass oscillates back and forth on the spring, by all means, it definitely does still happen because it would go back and forth. But this is an object being launched from the spring platform.
So it's just
So as soon as the spring reaches its full extension, the mass is going to separate from the spring, and the mass is going to go off on its own, which is why the mass then has kinetic and potential there. Tristan.
And is gravity always potential or like it's going kind of?
Gravity is always potential, because potential energy comes from either height or the state of being. And the state of being meaning a compressed spring, an extended spring, or an object that you've torqued. When you release it, it'll start to unwind. That's rotational energy we'll get to, but the same concept. You're storing energy by twisting, by compressing, by pulling, by moving something to a higher height. You're storing energy in it. It has the potential to become kinetic energy. Okay? So that's gravitational is always potential, yes.
It's like
And it's mgh at that point, absolutely. Now, here's the tricky part. At the max height, what kind of energy does it have? At max height, what kind of energy? Mondo. Good. Chris, explain further.
There's kinetic energy in X direction.
That's the one that students always forget for this problem. It still has kinetic energy at max height. Remember, because it's still moving horizontally up there. What is it going to have more of, though? Or I should say not more of. What is it going to be kinetic energy-wise compared to the previous state in blue? Red or blue, which will have more kinetic energy, red or blue? What do you think, Sheriff?
Blue.
How come blue will have more kinetic energy?
Because there's less potential energy, so it has to be more kinetic energy because of the
Conservation of energy.
Right.
So Chip is using deductive reasoning, which is smart. He's saying, you know what? At this location, there's less potential, and there's more potential up here. So the kinetic has to be the opposite. I would agree with Chip. Can I get another rationale for it, though? M.
Because where it's blue, there's velocity in the x and y direction, and at the top there's just velocity in the x direction.
You see? So they both argue, those arguments agree with one another. So you could say that the velocity is both vertical and horizontal here, but when it gets to the top, there's no vertical velocity, it's only horizontal, it's only Vx.
If it's shot straight up, there's no kinetic.
Say again?
If it was shot straight up, there'd be no kinetic, right?
If it was shot straight up, absolutely not. Just like in the lab you guys did. You did the lab with the launcher straight upward again. So when you guys pulled back on the spring and you let go, when it reached the top, now yours kind of deviated left to right, if we recall, but assuming it only went up and down, when it gets to the top and it stops, it's all potential. Because it's not moving left to right, it's just going to fall back down. But for one that's launched this way, at the top, it stops vertically, but it still has Vx at the top over there. Yeah?
But wouldn't you if you're using the kinetic energy from the x velocity, but then you're using the gravitational potential energy from the y velocity. are you not?
The gravitational potential energy comes from mgy. There's no velocity involved for gravitational potential energy. So let me jot it down what you would be doing, okay? So in the very beginning of the problem, let's write our formula. We'd have mgy initial plus 1/2 kx squared. That would be the beginning part. That's the energy that we have. Then the kinetic portion is going to be 1/2 mv squared plus 1/2 m, and I'm going to call this y2, the second height. Notice the v, I just call it v squared. I don't say vx, I don't say vy. I'm talking about the overall velocity in blue. Because remember, there's velocity in both the x and the y direction. I don't want to use those velocities separately and have to calculate the kinetic in the x, the kinetic in the y, and figure that out. I need to know what the overall speed is there. So I figure out the overall velocity, which is the resultant of those. Then in red, this becomes 1/2 mvx squared plus 1/2, plus mg. I'm sorry, guys. I don't know why I'm writing 1/2. I'm losing my mind. This is not. Sorry. Start. Backtrack. I'm getting you confused more. UG is MGY.
Okay.
Is MGY. Sorry, Matt. I apologize.
No, I think I understand. I was just
That's
I was
that's
thinking
me.
of it as like X and Y value, like it is when it's not that.
It's not for the potential.
Yeah.
For the potential, it's only based on the Y.
Yeah.
Yep. And then this is going to be MGY3. I'm just using 2 and 3 to indicate different heights, that's all. Y2 is different than Y3. Sorry, I don't know why I was just writing 1/2 MV squared, I guess because I had 1/2 KX squared as my head. So those are the 3 points we have to start. Now, what else could we think about? We could also think about down at the end over here, right before it impacts the water, when it's at what we're calling to be ground level. Okay, what we're calling to be ground level there. What can we say at that moment? What can we say at that moment? Chip, what do you think?
Minimum of potential energy, so 0.
So it's got 0 potential energy there, right? And what kind of energy does it have there? Only kinetic. Let me use yellow for that.
Will it only be vertical at that point? Only vertical kinetic energy? I mean, based on your graph?
If an object is launched at an angle, it's always moving which way?
Horizontally.
So could it ever be vertical velocity? Always going to be at an angle. Think about it. And that's a question I either gave you guys or the other honors class at one point in time. If an object is launched at an angle, after a long time, it's going to look like it's falling straight, right? But technically, it's always moving to the right because it always has horizontal velocity.
So is that 1/2 MV final squared?
So that is 1/2. Yep. This would be 1/2 mv final squared, or I'm just going to put v squared for now, at that moment, the velocity at that instant. Now here's the issue we're going to run into now, though. If I suddenly introduce this part of the problem where it hits water, right, and it goes underwater. If it goes underwater, what kind of potential energy does it have now? Down here. It would have negative potential energy? So what I think makes more sense, instead of calling the ground, what do we do instead? We could say, let's call this ground level actually. And as a result, this would still have potential energy at this point. Again, if we call ground level where it's eventually going to end up, it just makes life a little bit easier. And it helps us to recognize, well, you know what? All of these heights have some y value. Even this location has some height to it. So we would have to know the value y4. And this is the value y4 right here.
So wouldn't that change all the answers above?
Absolutely, of course.
So like on a problem, how would you know which to use typically?
So that's a great question, Tristan. How do you know which location to make the bottom? The lowest point, make the bottom. Always, because it makes life easier, right? Think about it. If an object is eventually going to end up on the ground, make the ground u equals 0. If it's going to end up in a body of water below the ground, make the bottom of that body of water u equals 0. Wherever the problem is going to be lowest, make that u equals 0. Does that make sense logically? Okay, this is a technique that I learned in high school that your book's not necessarily going to say to you. You're going to just almost go the ground 0. And then yes, you can do that, and then this is negative potential energy. But do you want to have to deal with that? No. So you just make the lowest position of the object for the entire problem u equals 0. So if this object, right, let's say it was sinking, and then somebody just held on to it, or I don't know, they got caught by a fish swimming across, then the u equals 0 would be right here, where it eventually stopped, the end of the problem. Maybe it's a body of water, and I ask you only about the location of it 2 meters into the water, which is right here. Well, then that's your u equals 0 line right there. So it really depends on where the problem ends, or where it ends. So what is y3 really? y3, let's take a look. y3 was the max height, wasn't it? That's what I was denoting earlier for y3. So y3 is really going to be y4 plus h. Take a look at my diagram. The height for y3 at the maximum height is h plus y4. Because we're now calling the green line ground level. Because the green is ground level, the entire distance from, again, the bottom here all the way up to the top there, that is Y3. Does this make sense what I'm saying right now? How would I denote what the value of, well, I'd have to be given something in the diagram, right? Yeah. I'd have to be given part of the diagram. But the idea I want you to see is that if you're going to move the lowest potential energy line lower, then the potential energy at this height is not any longer going to be just this value here to here. It's going to be the height plus Y4. Those two things together give you the height from the bottom to the very top, which we're going to call Y3, which goes in right there. Now, this is the part that a lot of you struggled with afterward. What happens after it hits the water? What happens? What happens? Water does what to anything compared to moving through air? Due to drag. Yeah, drag. That's it. Drag. Drag is caused by what? An object moving through a fluid. Now, the air is a fluid, but we can say that while moving through the air, the frictional losses were negligible until it hits the water suddenly, right? And when it hits the water causes it to slow down so that when it hits the bottom of the surface here, it only has a velocity of, say, 0.5 meters per second. So let's say the velocity is given as 0.5 meters per second right there. And it hits the ground, and when it hits right here, it's only going to have the what? The kinetic energy that it had the moment before it hit. Why won't it have potential energy there? Yeah, it's at the origin, what we're calling, or the potential energy reference line. It's at the zero line. So it's got no potential there, it's only got kinetic. Well, how is it possible, tell me, right? How can I go from having kinetic and potential in the yellow state right here to suddenly only having kinetic and the velocity being less than what it was here? How is that physically possible?
You lose energy.
You lose energy due to, again, drag, which is work done by friction. Your book is calling it, find the work done by friction. Drag, the amount of energy lost. So let's say we knew that while it was moving down here, we can denote that with WF to show that it's losing energy. It's losing energy due to friction. So, a couple of asked questions like this. Which side of the equation do I put the work done by friction? Or where do I count for work done by friction? Use logic. Use common sense. In the yellow state, it's got kinetic and it's got potential. Then at the very end of the problem, it's only got kinetic. So where will the work done by friction go if we consider it to be positive? If we consider work done by friction to be a positive amount of energy, which side should it go on in this equation? On the right, to balance out what we lost here, right? But if we're going to consider the work done by friction to be negative and use FF times D times the cosine of 180, where the work done becomes negative, then you should put it over here. Because I think, Chip, you've been asking this question a couple times now. So my recommendation is to recognize and use common sense. If the work done by friction is going to go down as a negative quantity, put it there. But if the work done by friction is going to go down as a positive quantity, then put it over here. So the reason I'm putting absolute value bars around WF is because, yes, a lot of you are right. The work done by friction is considered negative work. It lowers the kinetic energy of the object. That's what it's doing. It's physically decreasing the kinetic energy of the body. So that's why this ends up being a negative quantity, plus this quantity makes K be a lower value in green than it would have was from the K and the U in yellow, because work is negative. Or I can move it over here and say, oh, you know what? I had all this energy, I've only got some left, so that leftover that's missing must be the work done by friction. Now, one more follow-up to this. That gives you the work done by friction. What units does the work done by friction have? What units does the work done by friction have? Is it joules? Energy, right? But if I asked you to find the force of friction, or the average, I would say. I wouldn't say force, but the average, because force of friction is going to change through a fluid, right? As an object goes faster, remember drag gets higher, we did that with the coffee filters. So I know that this is going to be F times D, but F is going to change as it gets faster or slower, etc. So I'm looking for an average force F, and I need to know the distance D. So if I wanted to find the force of friction, I would go to the next step in this process and say, this was kinetic at the end, right before it hits the water surface, plus potential right before the water surface, equals kinetic at the bottom of the ocean or water, plus the force of friction times the distance. So I'm solving for this if I know D. Well, what is D equal to in this problem, folks? What is it equal to?
Y4.
Awesome job, Tristan. Y4. It's the distance that it is slowly going through the molasses or the water or whatever it is. The distance that friction acts on it is equal to Y4 because friction starts acting when it hits the water. This is analogous to an object going down a ramp. Frictionless, 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 and then it hits a straightaway where there's friction on the floor suddenly. It's the exact same problem. Literally the same problem. I could drop an object down that ramp and say the ramp is frictionless, and when it hits the floor there's friction. It's like hitting the body of water where there's friction suddenly. The floor is the D value now. The distance it travels along the floor is that D. It's no longer the vertical distance of the water. I can still solve for FF. For the ones that travel horizontally, I could go further. And I could replace FF with what? What is FF really? It's, what is it? Yeah, it's mu times Fn. And what's Fn for a lot of these problems if it's sliding on a horizontal floor?
MG.
Yeah, Fn turns out to be mg for a lot of them. So this can go a couple steps further if we have a problem. If we had a problem like this. Okay? Take a look. The object is released from a ramp. It slides down. It's about to hit the floor there. And then it starts to slow down when it hits this frictionless or friction-filled area. This is a good example where we have maybe kinetic and potential in the very beginning at the top here. Right? All kinetic and potential. Look, that's right here. Kinetic and potential. And then, when it gets to here, we've got kinetic at this region. And then it's going to lose a lot of energy due to work until it gets to the very end.
And K plus UG is equal to 1/2 MV final squared minus UG Y4. Like, is that why it's yellow? Because it's equal to
This yellow up here, Tristan, is this yellow here, which is this, which is this, which is this right here. But I'm saying for this problem, it's a new problem with a ramp. At the top, if you gave it a little push, you would have kinetic and you would have gravitational. At this moment here, you would have only kinetic. But as it's traveling along the floor, if it's still moving, you still have some kinetic, which is this, and you have some frictional energy loss, which would be the friction on the floor.
positive.
What are we talking about, Tristan? Yeah.
Frictional energy loss. I just don't understand how it's.
So if we think about it, if I have 10 joules here of potential and kinetic combined, and then there's only 7 joules of kinetic left here, where's the other energy? The 3 joules due to work done. So if I'm doing it this way, and I think of this as 10 joules, this is 7 joules, this has to be 3 joules of energy lost to friction. And then if I know that's 3 joules, I could say, well, that equals mu mgd. If I know mu mg, which is given in the problem, I can find d. Or if I know mg and d, I can find mu. But the idea again is that I'm trying to give you guys the concept of thinking about energy at given instances along the way. In the beginning, it was all potential and kinetic. Then it was mainly kinetic here, pretty much all kinetic here. And then as it's sliding along the surface before it stops, it's still kinetic and partially some of it lost to work done by friction. So at any instance in time, you want to be able to identify what types of energy there are. But the whole governing thing is what? What's the governing thing that comes back to all of this?
Law of conservation.
Yeah, it's always going to be equal at any moment. So the moment in the very beginning of this problem, right? If I go back to this one, the moment in the very beginning, this You could set this equal to this at the very end. You could set this equal to this right here. You could set this equal to this right here. At any instant, the energy is constant. You're never losing or gaining. You're only transforming energy. So the conservation of energy can be applied to any problem. So if it were me and I were taking the next 2 days to study a little bit more, which you definitely should do, because you asked me for that extension, I would definitely go through the part of like starting problems, just working through them, maybe even not with the numbers, just looking at problems and trying to identify what type of energy you have at what given moment along the way. I think that would be a good starting point. Hey guys, what happened to Spencer?